Good evening, everybody. Welcome to the latest installment of our EcoFlora virtual seminar series. My name is Lydia Paradiso, and I'm a doctoral student at the New York Botanical Garden and a graduate fellow with the New York City EcoFlora project. EcoFlora is a community science project with three main goals: to investigate urban ecosystems and urbanization, to support open source biodiversity data, and to increase the understanding and appreciation of plant life. To date, over 34,000 observers we're edging closer and closer to 1 million observations of plants and their biotic partners in New York City that are posted on iNaturalist. You can explore all of these observations on our project page on iNat, which I'll link in the chat in a second. We also every month sponsor an EcoQuest challenge, which encourages New Yorkers to observe a particular species, group of plants, or interaction and post those onto iNaturalist. This month's challenge, August Aquatics, focuses on wetland plants. Wetlands play a crucial role in supporting wildlife, safeguarding coastal communities, and mitigating urban heat island effect. New York City's 5,650 acres of freshwater and saltwater wetlands represent less than 5% of our historic wetlands. These vital areas serve as habitat for 156 species of native obligate wetland plants, which are plants that almost always grow in water, including swamp rose mallow and broadleaf cattail, as well as 9 state endangered species. So far this month, 28 species have been observed, including at least one of the state endangered, which is really cool. If you want to receive emails from us about upcoming EcoQuest and virtual and in-person events that we'll be having, you can join our mailing list by following this link that I just posted in this chat. So now I'll turn it over to Tomi to introduce our speaker for tonight.
Hi, everybody. My name is Tomi. Before we begin our seminar, we'll start with a land acknowledgement. So I want to begin by recognizing the original people of this land, the Lenape, as well as their deep connection to the Lenape homeland. As a representative of an organization dedicated to advocating for the more than human world, it is imperative to acknowledge the original stewards of this land, the Lenape, as well as the settler colonial genocide perpetrated against them and other indigenous communities. It's also very important to recognize the resilience of the Lenape and all indigenous communities who still today continue to resist erasure. I'm going to drop a link to the donation tab on the Lenape Center homepage. The Lenape Center is an organization in New York City that focuses on bringing back Lenape culture and acting as a place of conservation and also where people can share their cultures. So the reason we're all here tonight is to hear our speaker, Dr. Jillian Gregg. Dr. Gregg is the executive director, principal investigator, and founder of TERA, a nonprofit research foundation focused on plant ecophysiology and global change. She has worked previously at the U.S. Environmental Protection Agency and is also currently lecturing on environmental topics at Oregon State University. Jill received her master's and bachelor's degrees from the University of Utah and her doctorate from Cornell University. Tonight, Dr. Gregg will discuss her work determining the effects of multiple pollutants and elevated temperature, CO2, and nitrogen deposition in New York City on cottonwood clones, growing in urban and rural environments. Please feel free to enter any questions or comments into the chat as we go. At the conclusion of the talk, we will go through as many questions as we are able. If you have a question or comment and you would like to ask it verbally at the end of the talk, you can use the raise hand feature or note in the chat, and you will have the opportunity to do so. Also, if you are unable to stay for the whole talk or would like to share with others, the recording will be posted on the New York Botanic Gardens YouTube channel and EcoFlora playlist. Lydia will drop those in the chat. And now I will hand it back over to Dr. Gregg.
Okay, back over, but I guess that's the first time to me. You said Dr. Gregg? I'm up. So I am so excited to hear that you guys are in New York City and interested in the natural heritage that you have. And that is where I began. But I have been out here on the West Coast for a long time. And so I'm I'm thrilled to hear what questions you have. Especially was excited to hear that Lydia's at the New York Botanic Garden, which was one of my urban sites. And I had certainly a lot of collaborators there also. So with that, I think I'll just get into the talk. Here we go. Let's see. Okay. You know, you guys already introduced me a bit, but I'm going to do a bit of my own introduction also. I grew up actually in Ohio, and often I follow other speakers who are talking about how beautiful the place they grew up is. But growing up in Southern Ohio, we were near this Ohio River with all the factories that are along the river and all the pollution. And when I was a kid, the Cuyahoga River caught on fire by spontaneous combustion. And it just seemed that everywhere that you looked, there was a fence, just the concept that there were places on Earth that you could go for days and days and never come to a fence. I knew that it existed, but I had not seen it. And I was, you may meet a lot of people from Ohio because we are looking to see other places. But it did instill this interest to understand pollutant and climate change impacts. And so I went to various places, but ultimately ended up at the University of Utah, where I did my bachelor's and my master's. But I had the opportunity while I was doing my undergraduate, because there's a major ecology program there, where I got to work in the tropical rainforests of Panama. And then I did my master's degree, and I worked in the Grand Canyon Desert Southwest area. And that was fascinating. But I was seemingly, ecologists were always going to these pristine environments to study ecosystems in their natural states. And really, I wanted to know what was the impact of humans on these environments. So I ultimately ended up doing my PhD at Cornell University, where my research focused on pollution and climate change impacts in New York City itself. And given that research, when normally I tell the story about where I go and what I do, and I never have the time, and I say, I don't have time to tell you about that work, so let's just get on. So I'm glad that in this talk, I really will be going back and explaining the details of what I did in New York City. But because I did pollution and climate change research there, I really, Cornell wasn't the hubbub of pollution and climate change research at the time. The US EPA was. So I moved from my dissertation at Cornell to the US EPA in Corvallis, Oregon, where I actually was doing a lot of stable isotope work, but then they had this multi-million-dollar global climate change research facility that, a year after I got there, they had to close it down. So I wrote a grant to the Department of Energy to reopen this facility and do a decade worth of research. And because the EPA can't take DOE money, that's why I started a nonprofit research company. And so I ran this global warming experiment for a decade before I moved over to OSU and started teaching climate change to the masses. I have over 1,200 students a year. So as you're thinking of questions, if you have any climate change questions as we go, I'm happy to address those at the end also. But as far as an outline, I'm going to talk mainly about the New York City research, and I'm going to talk about how that led into climate change research. Although given time constraints, this will probably be cut quite short. And then I'm just going to have one slide telling you about my interactive climate change e-workbook that's available if you know high schools or colleges that want to learn climate change in an interactive way. It's been quite useful in teaching about climate change. So let's go to New York City research. There you guys are. Are you guys all pretty much in New York City right now? It's not very interactive. I'm used to talking to my classes. Some of you are. I'll presume some of you are.
A good amount, probably.
What?
Probably at least a very good amount, probably.
Okay, great. So here I am. What I'm saying is I did all this research in Panama and the Grand Canyon, and I really wanted to know not just how natural ecosystems work in the absence of humans, but if you're going to study if ecology is the study of environments, of organisms and their environment. And, the most interesting thing that's happening right now is the changes that humans are making on the environment. Then the most interesting thing to me has always been, what are the impacts as the humans change the environment? How is that going to be changing our ecosystems? So my overarching research question that I wanted to address for my dissertation was, how could this continued increase in multiple different human accelerated environmental changes affect these pristine environments in the future? And at the time, people were just, so this was in the 90s. And so people were just moving on. Well, rather than just studying ozone impacts or heavy metal impacts, we need to look at the combined effects of two factors. So there are all these studies coming out like, oh yeah, well, you look at two factors and the combined result is never just the effect of an individual factor. There's all these interactions that happen. So it's like, well, great, I can't just pick one factor and study it, or two, or even say maybe three factors and look at all of the interactions. I'm never going to know what is the actual net effect of all the different things that could possibly happen, and what's the relative importance of these different factors. So I went out on a limb and made my committee not that happy. And I said, I'm not going to do standard ecology. Like, this is my chance. I'm going to go and do what I think is going to give me the most information. So what I wanted to do is use New York City as my microcosm of global change. You guys have the high pollution, and you have hot air pollution, high soil pollution. You have high CO2 concentrations. You have warmer temperatures. You have increased nitrogen deposition. You have all the different factors are all changing all at the same time. And there I was at Cornell, not too far away. And I thought, I'll use this as my microcosm of global change. But, most people, they're not your group, and they think it's all buildings in New York City. But of course, there are these remnant forest stands that still occur, not only in the city, but also in the country on the same soil series. And what I wanted to do is utilize really these remnant forests to understand how they're responding, and so how a rural forest could respond in the future. So here's some, this is, I believe, it's an old picture, but I'm presuming that this is going to be Central Park, and these are two rural stands. Okay. So yeah, so I was using the gradient approach. So whereas normally you use a successional gradient to say, how a younger ecosystem is going to look in the future, I was using the urban to rural gradient in the same way to say, how could rural environments look as pollutants spread in the future? So it's a gradient approach, but still you have, this depiction of, there's still different species with just different genetics when you look at the actual forests. So I wanted to hold genetics as constant as possible. And you'll see in the next slide, I use this fast growing genetically identical cottonwood clone. And I grew it in urban and rural sites. And I wanted to know first, well, what is the net effect? How much worse are they going to grow in all that urban pollution? What is the relative importance of changes above versus below ground? Because the reason I was driving my committee crazy is you can't study everything. I'm like, well, I'm going to give it a try. So I wanted to know the net effect, and given the net effect, I'm going to have to tease apart which factors are important. So then determine the relative importance above and below ground, and then given those, what are the which factors had the greatest impact? So here we go. There we go. So I predicted, of course, that plants would grow less in New York City. I thought both the atmosphere and the soils would both have a detrimental impact. And then we would figure out which factors were the most important. Okay, so this is my genetically identical cottonwood clone. It's a fast growing tree species. So I want, the faster it grows, the bigger growth differences I'm going to be able to see in the time period that I analyze it. Then it was also already known to be pollution sensitive, so it's gonna have some response. And I wanted to grow them actually in open field sites. So I didn't want the growing season length to be an issue. So what I did is I planted these, I found 2 urban sites and 2 rural sites on each of 2 gradients. So the Long Island gradient I took because it's the same latitude, and so the same climatic region, but different urban and rural sites. But it's always good to have a second transect from the same city. So I had also the Hudson Valley transect. Of course, the winds approach New York City from the southwest. So the Long Island was a nice steep pollution gradient, and the Hudson Valley was more of a second transect. All right, so I could plant these cottonwoods in these urban and rural sites, but I needed to know the relative importance of changes above and below ground. So what I did is I had located all of these urban and rural forests that were on the same soil series, both in New York City and out Long Island, and then a different soil series from the New York Botanic Garden and up into New York State. And I went to all these different forests and I collected soils. And I collected the soils and I sieved out the roots and the large roots in the rock. So down to 1 inch, everything went through a 1 inch mesh. And then I put those soils in pots and carried those pots to all the different sites. So within any one site, I would have plants in 2 different urban soils and 2 different rural soils. And so I could say, do plants in the same site always grow worse in the urban soils? But I could also ask the question, within any one soil grown at all the different sites, how much worse do plants grow in New York City? In addition to these forest soils, I also had one soil that was a potting soil with added fertilizer. So I would get the maximum growth differences between the different sites. So this is collection of soil and sieving of the soil in the New York City parks. We got to be there at dark one night, and my helper, I'm like, we got to get out of here. It's dark. We're in the forest. And she's like, but we're the ones with shovels. Like, we are the weirdos. But anyway, we did make it out. And a nice German Shepherd that I brought with me everywhere. But the soils, this is actually an urban park, and we went around and we got permission, so people knew we were doing this, and we transported the soils everywhere. And so then we didn't want the soils to be warmer because they were sitting in pots on the top of the ground. So everywhere I went, I dug all these holes in the ground and surrounded it in chicken wire so they wouldn't get eaten, and planted them in. And then they also had, so they're all in open fields, so they receive full sun all day. And they had drip irrigation, so they had as much water as they needed. Okay, so there it is. There's at the beginning of the season, but beginning of the season, so that would be beginning in June. And so that it was already the growing season at all sites. And then I harvested them in early September so that the growing season was still going at all of the sites. So when you see growth differences in contrast to other urban-rural studies, where they do look at the actual forest species and leave plants year-round, in those studies, you have a real growing season difference. In my study, I completely obliterated any possibility of growing season having an impact. So here we are, and this is the potting soil with the added fertilizer, so that's why you see the perlite in the top. Okay, so here's a rural site. This one's up at the Institute of Ecosystem Studies in Millbrook, where my collaborators were, Mark McDonald and Clive Jones and Stuart Piggott, who are all, the beginning of the urban-rural transect studies from out of the Millbrook area. So that's a rural site, and this is one of my urban sites. This is at Con Edison Fuel Depot in Astoria, Queens. And I had a van to help transport things around. And you can see more Manhattan off through the smog. Oh, so what do you think happened? I'm showing you the results in pictures. And here we go. Like, this is what we found. So have a quick look. Like I said, I harvest them in September, so I could bring them all to the same spot and have a picture of all of them side by side before just harvesting them and weighing them and making graphs. So what we see is that so sometimes these plants, they grew worse in the urban soils, but sometimes they grew better. There was not a consistent soil effect. Certainly in the potting soils, they grew substantially more. But no matter which soil I grew them in, they always had twice the biomass or more in the urban sites. And that was consistent across transects, across years. And I was like, oh no, I'm going to do the study that everyone's going to say pollution is good for plants. But these are the results. And then this is more cutting them down and weighing them and looking at the shoot biomass. And so this was consistent for 2 different transects and 3 different growing seasons. These plants were always growing substantially more in a city. So there's really no debating it. So I have to say, even after that first season, when I came up with this result, my committee was a lot happier. They're like, oh, you're actually seeing something. So you can keep on with this project. So I don't know how many grad students will be in the audience, but so let's move on from that. And also with the roots, both the roots and the shoots were growing more in New York City, and not a big difference in the root to shoot ratios. So that was my question, what's the net effect? And I had really thought that plants were going to grow worse in the city, but no, they're growing double in New York City. And what I thought both the atmosphere and the soil would have an impact, but really changes above ground were having a much bigger effect than changes below ground. So now I could go and ask the question, let's go back to individual factors and try to suss out which of the different factors have the greatest impact in causing this change. Okay. So here we are, so this section is going to have 2 parts. Which factors varied, and then I do experimental manipulations to exactly mimic the urban and rural environments to see if I can recreate what I saw in the field. Okay. Okay, well, we think we're good because we have a net effect and there's still many factors above ground. One point that I didn't highlight when I talked about my site selection, and you guys might be interested in those sites. My rural sites, I had the main point about all these sites is they all had Department of Environmental Conservation air monitoring stations. So I was able to get the data, but the climate and the pollutant data directly from them. So going out Long Island, I was at Eisenhower Park and Long Island for the Cornell Agricultural Research Center and Riverhead, and and also at Brookhaven National Lab. And in the city, I was at New York Botanic Garden, the Bronx sewage treatment plant in the South Bronx, the Con Edison Fuel Depot in Astoria, and actually I counted Eisenhower Park as urban. It's a little bit further out, but counted that as urban. Okay, so these are all the factors, and there's still tons of factors to figure out. But it turns out, I said before, they all got they all had ambient precipitation, but they also had these, they were irrigated. And so they all had plenty of water. They were all in open field, so they got full sun all day, and humidity was fairly similar between the different sites. So we ruling out environment as much as possible. Then most pollutants are going to have a negative impact. And so they grew, and most pollutants are higher in the city and they have a negative impact. And so those are not going to be causing the double of growth in New York City. But certainly nitrogen deposition could cause increased growth, but the fertilized potting soils had 3 orders of magnitude more nitrogen than was deposited to the urban sites over the June, July, over the 3 months that they were in the field. So nitrogen deposition and even the fertilized potting soils with all that added fertilizer, they were growing double in New York City. So that couldn't account for what was going on. But as I said from the beginning, we do have elevated temperature and elevated CO2 concentrations, and either of those could very likely account for increased growth in the city. In fact, at this point, what I had determined is probably what's going on is in the city, it's warmer, you have more growing degree days, and so more growing degree days are going to make the plants grow more. And that's going to be the result of my whole dissertation, is that growing degree days make plants grow more. But I still needed to work my way down to that by performing the experiment. So I did this growth chamber experiment that had just elevated CO2 comparable to the city and the country, and elevated temperature comparable to the city and the country, and then the combined effect of both. And I guess I didn't show a picture because anyway, all of those results were just no difference. And you'd be kind of surprised with CO2. You think, well, higher CO2, they're going to grow more. But this same cottonwood was used in the Biosphere 2 project, where they were looking at the impacts of elevated CO2 on cottonwood growth. And they used a doubling of CO2. My CO2, I only used an increase of 50 parts per million. Based on some corn that I had grown in the city and the country, and look at the stable isotopes to estimate how much higher the CO2 concentration on average from a plant's eye view would have been in my specific sites. So I grew up at 50 parts per million higher CO2, and that didn't account for increased growth. But even when the same clone was grown in doubled CO2 in the Biosphere 2 experiment, they also saw no effect of CO2 on this particular species. So I feel confident in the CO2 result, and that's where we left off with it's got to be temperature. But then the temperature, where I have the data, I had the data from the DEC, and I was able to replicate not just here's the average daily temperature and here's the average rural temperature, but I did the 15-minute by 15-minute differences throughout the day between the city and the country. And so I looked at the real diurnal profile and saw no difference, no impact of temperature. Okay, so I was like, okay, maybe I really needed to change my mindset. Maybe rather than figuring out which factors are accounting for increased growth in the city, I actually need to flip the question around and say, which factors are accounting for reduced growth in the country? And the one factor that I have not brought up yet here, and I guess my controls aren't in your guys' way, but I can't see that. Okay, the main factor is ozone that I haven't brought up. And so we think there's all these ozone degree days in the city, or ozone warnings, and don't go outside, ozone alerts. And so we think of ozone as being highest in the city. And but when you actually look at the ozone data, because these were all grown at DEC sites where those data were collected, this is just 2 sites. And the average daily ozone concentrations are actually much higher at rural sites than they are at urban sites, which comes, So what I needed to do then is say, if ozone is higher at these rural sites, is it that the higher ozone in the country was causing the plants to grow less? So I was able to take advantage of an ozone study that was being performed at the Boyce Thompson Institute at Cornell, where they had ambient 1.8 times ambient and 3.0 times ambient ozone concentrations that were representative of urban, 1.8 times higher rural, and extreme high ozone concentrations. And I was able to grow the same cottonwood clone in those chambers and see what would happen. And I found that when I grew them in the 1.8 times ambient ozone, which is how much higher the rural ozone was compared to the urban, then the plants did grow half as much, and there's a real step increase. So even when you got to 3 times ambient ozone, they were still not growing well. So then if you just go back to that was true for both roots and shoots, did the same thing. If we go back then to the urban and rural data and plot it versus, we thought it was temperature would explain everything, the final season biomass for the different years and the different sites, you would think it would all line up with growing degree days. But in effect, it didn't. It was strongly linearly related to ozone exposure. And this is the 12-hour mean ozone exposures. So it seemed that ozone was the main thing. So what was fascinating really about this study is that we were really focused on urban factors and how that would make plants grow worse, but ultimately found that the higher rural ozone exposure really is accounting for reduced growth in the country. Okay, so so then you have to go back and think, well, did we just pick certain sites right outside of an urban center where ozone was just so high at those sites that of course you see that effect? So what I did is I looked at the mean annual ozone concentrations throughout all of New York State, and knowing that the winds are approaching New York City from the southwest and blowing pollution up northward, that we would have thought we'd have a stronger lower ozone concentration, lower pollutants in the country. But anyway, if you compare all of these numbers, and I have a table in the next one, these urban values are actually lower than anywhere in the state. So that made me want to look, I want to show this next slide first. If you look at it as a table, here we are, these urban sites are very low compared even to, we have Olympic National Park, Redwood National Park, Yellowstone, the South Pole, Barrow, Alaska. Like, it turns out when you look at the average 24-hour values, urban ozone concentrations are lower even than the South Pole. And then it's not until if you look at the peak ozone concentrations that if you look at the peak ozone concentrations, New York City is lower than if you're at the bottom of Whiteface Mountain there in New York. And it's lower than any of these rural sites. It's the World Trade Center, I guess, is upwind, and it's not in that real heart of the city. And so the real heart of the city in Queens and Murciana, we're seeing these really low concentrations. But if you compare these peak values to the Olympic National Park and South Pole, they're certainly higher in New York City than those. And by peak, I'm going to go back to this previous graph and explain that. Okay, so what I'm saying is that there's these holes of lower cumulative ozone exposures in not only just in New York City, but all cities. Okay, it's ozone experts are like, well, we knew that long ago. In fact, when they make the maps of ozone across the United States, they have to get rid of the ozone data the urban data in order to make those maps. Otherwise, they'll underrepresent the ozone exposures because they know that the cumulative exposures are lower in the cities. So actual ozone experts are not floored by this. This is just known chemistry. And the idea is that in order to create ozone, you have to have some combustion reaction. And so your combustion reaction, the main molecules in air are N2 and O2. And when you get N2 and O2 in a flame, then you're going to create NOx. And that NO radical is going to interact or react with O2. And that will give you an O radical. And that O radical then reacts with O2, and that gives you your ozone. So that's what's normally happening in rush hour in New York City. But once rush hour is over and you've had these high ozone concentrations, then rather than the NO interacting with O2, it actually interacts or reacts with the O3 and turns it back into oxygen and NO2. So if you look at a daily course of ozone in New York City, and you compare it to one of these rural sites, that the urban sites get much lower at night and past rush hour points in time. And at rush hour, you may have similar levels or even higher levels in the city. But as soon as you look at the cumulative values over some threshold, you can see that the area under an urban curve is always going to be lower than the area under a rural curve. And for plants, it's the plants are outside all day long. And so it's well known amongst plant physiological ecologists that it's the cumulative daily exposure that's the most important, rather than an individual 1 hour peak that it's high. So, and actually human and mice studies they haven't done as many long-term cumulative exposures, but I've spoken with those communities and they believe, since that the impacts of ozone on asthma studies are done at these rural camps where children are, they believe that the rural ozone probably would impact humans similarly. But this is a plant study. But I'm just saying, when you're thinking you're in New York City, I did live in New York City for a while. I always thought, I got to get out of the city and go into the fresh air on Long Island to the beach. And just know you're actually getting a larger cumulative ozone dose when you go out there. Okay. So fascinating. I just like to say, I don't know what this. Oh, good. Okay. So I just want to put a shout out for reduction. There's reductionist ecologists that we do need to know the effects of every individual factor in order for these more holistic studies to be done, so that we can work backward and utilize that data. But we also need these more holistic studies that really determine what is the actual net response and work backwards to determine the relative importance of different factors. So for instance, if we had not done this study, we would never have predicted that plants are going to grow double in New York City. Would not have predicted that. Then if we had predicted that they had grown more in New York City, we certainly would have said, well, it's got to be temperature, CO2, and nitrogen deposition that are going to account for increased growth in New York City. And that's an obvious thing. And, that's going to be important. But in fact, when we did the experiments, we found that none of those could account for that. And instead, we found that, and we would have thought ozone, we would have thought it's going to be highest in the cities. But when you look at that, it's actually highest in country, and that's accounting for reduced growth in rural environments. So that's the story in a nutshell of the New York City. So it does not negate the known detrimental effects of multiple urban pollutants, but they highlight the greater impact of secondary reactions that form the higher cumulative exposures beyond the city center. Okay. And it was a surprising enough result that they did finally publish it in Nature. After you have to go back and forth a few times and explain things, but they did do that, which is why you guys seem to have found the paper, because it did come out in 2003. So this is the 20-year anniversary. So thanks for being interested. Then it's a quarter of, and I could talk a little bit about how this led into climate change work, or I could open up to questions, and it just depends what you guys are feeling like.
Yeah, thank you so much for your presentation. It's really interesting that you got both an ecology lesson studying it and also a climate lesson. I think it was surprising for all of us to hear that ozone is higher concentrated in rural areas. Can you hear me okay?
I can hear you. Maybe if there's any questions in the chat already, I could answer those. And if there's not, then I'll talk a little about climate change.
So there are some questions. in the chat. Go ahead,
Okay.
Lydia.
Oh, sorry. Yeah, so there is one, which is my kind of burning question too, is do we know why this is the ozone is the levels are different? Because when I try to puzzle it out, is there something that they're not getting converted back as fast in the rural areas, or it speaks something to do with the way the wind is blowing? Like, what might be some explanation for that?
So it's that as soon as you have the highest concentration of NOx in the city, and you just don't have much NOx, and NOx is very short-lived, and so it doesn't blow out to the country. And so long as you're in the area where there's still NOx, then that back reaction with the NOx, even though you form the ozone to begin with, you then have the back reaction. But once that same ozone mass, if it's blown out to the country, there's no NOx there to titrate it down. And so it just stays in the air for longer. Yeah.
Chemistry is
So-
very interesting.
Yeah.
Yeah. So the compounds that are forming the ozone are in higher concentrations in the city, and those compounds also degrade ozone. So because the degradation
Yes.
is higher in the city than in the countryside, there's just more persisting ozone in the country or
Yes.
rural areas. Okay.
Right, and in fact, it's a concentration. As soon as the ozone goes up in concentration, those primary precursors actually have a greater affinity to the ozone than the O2, but in the beginning, there's not that much ozone that they could react with. So they start with O2, and then as ozone increases, then those get titrated out.
Looks like we might have to
Great.
take a step back about NOx, what it is,
Oh,
where it comes
okay,
from.
so NOx is, I mean, literally, even in forest fires, any combustion reaction. So the atmosphere is, so let's see, 70. I should have that number down. 70% N2 and about 21% O2. And so that's the bulk of what's in the air. So any fire, whether it's your car burning fossil fuel, or a factory burning fossil fuel, or a forest fire, or any fire in the air, it takes the O2 and the N2 and mixes them together. And so you end up with NOx itself is because NO changes, so NO changes to NO2 so quickly and rapidly that they call the combination of NO and NO2 is NOx. But the very first one that is formed is NO, and it's highly reactive. If I were a chemist, I would have put a dot on the top of the NO and the O and this O to indicate that they're these highly reactive molecules. And so once you have that, is that good? That's what the NOx is. So that's, yeah, it's really just having fire in air and mixing them together. And then of course, this whole thing is sped up if you have any like methane, or it's they call it RX. So any carbon compound that's floating around the air just it accentuates that reaction. So it makes it go faster. So that's why you hear that in Appalachia or whatever, the Appalachian forests, that there's really high ozone down there. And that's because these trees are emitting terpenes into the air, which serve as this an accelerator to the ozone reactions. Yeah. But also methane emissions also accelerate them. And it's really fascinating because with global warming, we are all worried about global warming, but the warmer it is, the more ozone is formed. And so we also really need to be aware about the impacts that global warming is going to be having on ozone, which this study shows of all the different pollutants, ozone seemed to be having the greatest impact. So
I guess the follow-up of that is, there's probably studies on why ozone why is ozone bad for the plants? What is it
Oh.
doing that's preventing that's
Okay.
going through?
Okay, ozone is a free radical. And so it just destroys cells. So basically causes cell death. That's so that's why it's not good for us to breathe it in. It's, there's the difference between stratospheric ozone and tropospheric ozone. Tropospheric ozone, the troposphere is down by the earth. That's the air that we breathe. And so when plants breathe it in, I don't have any pictures of beans. So I also grew beans at next to the cottonwoods in my urban and rural sites. And in my rural sites, the beans had these really, big brown spots of necrosis, just dead parts of the leaves. And that's why also ozone is thought to cause asthma, is because it destroys lung cells when you breathe it in. And so it's the primary, and then when you hear about it's an oxidant. So when you hear about eating lots of fruits and vegetables because they're antioxidants, then those are helping you to combat things like breathing ozone. So
Thank you for that.
Yeah.
If anyone else has any questions, we can throw them in here, or I would definitely be interested to hear you have a little bit more about some of the research that's going on now.
Okay. I'll continue on. So, great, right. And I just really think it's important, the footprint, we have all these monitoring and telling people not to go outside at different times in the city, and that doesn't happen in the country, and that's a concern of mine. And because we have this perception that it's a safe haven to be out and go to the beach on Long Island. But the beach, honestly, probably is getting some good ocean air rather than, probably even then it doesn't have the titrated down values that you would have in the city.
We do have something in here, another ozone question about the ozone holes.
Okay. Yeah, I didn't get back and explain it compared to stratosphere. So stratospheric ozone, that's if you put a hot air balloon at the surface of the earth and it has a thermometer on it, you let it go and you can record the temperatures as it flies up through the sky. You see, like as if you climb up a mountain, the atmosphere gets colder and colder as you leave the surface of the earth, both because you're farther away from the heat source, which is the earth radiating out heat, and you're also have less atmospheric pressure above you, so the atmospheric particles are not being squozed together, which is what causes it to be warm. So anyway, the atmosphere gets colder and colder with distance from the earth until you get into the ozone layer, and then all of a sudden it starts getting warmer and warmer with distance from the earth. And that's otherwise you just look in the sky and you don't really see a line like, oh, something's changing. But the reason we call it the troposphere and the stratosphere is because temperature changes from getting colder and colder with distance to getting warmer and warmer with distance. And the reason it's getting warmer and warmer with distance is that as the sun comes in, there's all these, the UV radiation, and the UV radiation is highly reactive, and it reacts with the O2 to make, so there's not N2 now in this reaction, it just breaks apart O2 spontaneously with the UV and creates oxygen, and that reacts with O2 to make ozone. And then that same UV can react with O3 to go back and forth, O2, O3, O2, O3, and that's what's all going on in the stratosphere. And those are all exothermic reactions. And so that's why you're getting that it's warm up there. And so the great thing about those reactions is that that utilizes up all of the UV. And so the UV doesn't come down and hit us on Earth and give us skin cancer. So that's why we want to have a stratospheric ozone layer. But when we developed these various, forever, we've been wanting chemicals that, that will last and never degrade. And so chemists figured out, oh, we can make all these chemicals that last and never degrade, and they can make us things like hairspray and and styrofoam and, various different things. And the chemical is called chlorofluorocarbons, CFC. And once we made those, they just started building up into the stratosphere. And those turn out that they react with the stratospheric ozone. They're light and they end up in the stratosphere, and they react with the ozone at the South Pole, and they take the ozone out of the air. And that was causing more skin cancer. So when you think of the ozone hole, that's completely different than climate change. It's a completely different environmental problem. And it's the problem where humans emitted CFCs, which reduce the stratospheric ozone, which allows UV light in and causes higher incidence of skin cancer. And fortunately for us, we had in the 1979, there was the Montreal Protocol, where all the nations on Earth decided that they would there was a international treaty to not emit CFCs, and so they've emitted other chemicals instead in the meanwhile, and those are being altered as we speak. We've also had the Kigali Agreement now, because a lot of the chemicals that we transferred to, they helped with the ozone layer, but they were really bad greenhouse gases. And so now we're transferring currently away from the one that's okay for stratosphere, but bad for what is a bad greenhouse gas, to a different chemical that's okay for global warming and also okay for the stratosphere. So it's taken a number of decades to get there, but that's a separate issue. So it's separate from this story because that's the stratospheric ozone, which we want, versus tropospheric ozone, which is bad because we're down here and we breathe it in. It's the same ozone, but the function in the stratosphere is helpful, and the function on Earth is cell necrosis.
We need to figure out a way to send it all up there.
Yeah, we do need to figure out a way to just send it all up there. That would be helpful. Do you have questions about that? But the other thing about this Montreal Protocol is this phenomenal example of a successful environmental treaty, international environmental treaty to help solve a global problem. And so it's something that we need to follow in figuring out what to do about greenhouse gases. Okay.
Looks like we got another question in here. Does ozone have any effect on the extreme weather events that we also see with climate change?
I have not heard of a link with that. No. I think with the climate change, these extreme events that we're seeing this summer, wow, it's really frightening. And the thought with that is that there's a lot of feedback loops on the climate system. It's not just, you think, oh, okay, well, it's warmer, and because it's warmer, that melts more ice, and the melting ice makes the ocean, more, you have less white surface on the Earth, so we absorb more heat from the sun. So that helps to add to the global warming. And that's one positive feedback loop. But I was just a co-author on a paper where we looked through and we found 27 different positive feedback loops, many of which are not being currently in the climate models. And so whereas we're making all our predictions of how long it could take to get to be 1.5 and 2 degrees Celsius and how much emissions we could have until we get there, we are concerned that the models, even though the models consider best case and worst case for how much CO2 we emit, they are not considering the worst case for these positive feedback loops that can accentuate the warming problem. For instance, say we warm, and so there's more forest fires, that puts more CO2. And so the CO2 causes more warming, but that warming causes more permafrost melt, which adds more methane and CO2 to the atmosphere, which causes more warming, which, all of these different feedback loops all go to warming, and the warming goes to all the 27 different factors. And it's, scientists are very concerned about the current leaps that they're seeing in extreme variables. And people are busy modeling it, but when you have to have multiple years of data to see something, you don't have an answer right away. But there's scientists are on high alert of what's going on.
Was the first author on this William Ripple?
Yes.
On the right one. Okay, I'm gonna post a link. The link is a little bit long. If anyone's interested in checking that out.
Yeah. Yeah. If you want to hear about that, I have a talk on that. But yeah, I think you're a plant group.
Yeah, speaking of plants, I understand why you chose the cottonwood. You said it grew well. And yeah, as long as it has full sun and water, it grows pretty well. It's sort of a weedy tree species. Do you have any indication of how other species that have different ecological requirements, like maybe a forest orchid that requires the mycelium in the soil, and sort of more sensitive species, do you have any indication if ozone is the most important factor for them as well?
Well, there was a follow-up study by a group at Columbia. And they legitimately, which is what I would think if I had read my study and I hadn't been the one who collected and graphed all the data, they're like, no, it's got to be temperature. And we're not going to use cottonwood. We're going to use the red oaks. We're going to use red oaks. So they did a similar study and they grew red oaks in the city and the country. And they saw the same thing of massively increased growth of the red oaks in the city. But they left theirs all winter long. And so I think if you have growing season longer, then that's obvious that that's an additional factor. So there are there's this whole urban rural comparison with plant growth has been, it's been done with grasslands around Baltimore, and they've seen, substantially increased growth and especially of ragweed in the city. And so they have all these studies saying that they think higher temperature and CO2 are going to cause increase in ragweed and to have more ragweed pollen going out there. But again, they didn't separate out the season effect and didn't separate out above and below ground and ozone. I'm the only one who has looked at ozone, and I would say that there's other people would say, no, we still, they still think it's going to be growing degree days. But as far as others, but so for both of those studies, even though they didn't, I envision that if they had just separated out and planted them in June and harvested them in September, they would still be seeing increased growth. Phoenix also, they've seen increased growth in Phoenix. Because there's all these different urban LTRs. So they've followed up and everyone's seeing the increased growth, but no one has really compared and had the argument. I don't feel very argumentative. So I think it's fascinating to see everyone's studies, but it would be great to get to the bottom of, the temperature, ozone, CO2 conundrum. Yeah. And, but the other thing people have asked in the past is whether, so this is great. Plants are growing better in the city, so we should all be growing these urban gardens and eating all the food. And I think we do need to be concerned about some of these other pollutants and if they're taking up heavy metals from urban soils. And so the fact that they're growing well could be good for carbon sequestration, but potentially you should just make sure what the soil nutrient contents or pollutant contents might be. So.
Yeah, it sort of begs the question also, like, what effects the cities are having on lands that are really, really far away. Like you said, the South Pole. Like, what are the effects of New York City on like tundric plants and things like that? It's just like a whole bigger perspective. You opened up a whole can of worms.
Yeah, it is. It's, yeah, people who normally, there's been studies saying, well, what happens just, downwind of a factory? But but even just seeing South Pole ozone is much higher. So, I mean, once it gets away from NOx, it just doesn't, when you look at the South Pole data, it's just a flat line throughout the day and throughout the year. It's not, it doesn't go up and down. It's just the residual of everything that ends up down there. So that's another fascinating thing to look at. But well,
I wonder what kind of effect something I haven't checked on the status in a while of the congestion pricing or the changes that they're trying to make with how many cars they're having in Manhattan. I wonder if that kind of this peak of rush hour, this would be kind of smooth out that curve. It would, I don't know how much it would take to do that, but it would be interesting.
Oh yeah, I mean, it's definitely directly related to amount of combustion of fossil fuels. So if are they just widening it, or are there really less cars?
I think that I'm not an expert on that. I know there's been a lot of different, that it's like to just reduce the number of cars that are in the physical space at certain times.
Okay, that's great. That's fantastic. And I've heard I mean, I probably need to visit New York City, but I hear it's clean and people aren't getting killed as often.
It is gorgeous.
Yeah.
I do also have another question. I think you might have mentioned it, but do we have any idea about where the ozone in the rural areas are coming from? Is it coming mostly from cars, or is it like forest fire ozone and other sources of ozone besides urban ones?
Oh, well, you have to have the NOx to produce it. And NOx is not, you don't ever have very high NOx in the country. So whereas they'll say in the Smoky Mountains, you have high ozone because you have the high tree RX emissions, you still have to have had the NOx to start this whole chain reaction off. So it's coming from any combustion reaction. You have to start with that. So those night pictures of the Earth, everywhere that you see light is probably producing ozone. And, including forest fires. Yeah.
Well, and laser printers also produce a very, very tiny amount of ozone, but they have ozone filters in them. Remember, I learned that a long time ago.
Okay, yeah. So, cool. I'm going to hear a little bit about where this led me in climate change.
Yes.
So there I was, and I had to write up my temperature doesn't make plants grow more in New York City work. I'm like, and so, so each of these came up to separate things, so I have an ozone paper, and then I have to figure out this temperature thing. So here's here's an urban temperatures from literally the data from a site. And then here's the rural temperatures. And so I'm looking at these and I'm like, okay, well, and I grew these cottonwoods in growth chambers that had these different profiles in them. And I saw zero difference. Like it was unbelievably the same. So it wasn't like, oh, maybe if I just had more replicates. No, there was just no variability, no difference. And so I started looking at these and I'm like, well, let's see. So the rural sites, they have, they have these, so it's warmer in the day. You should think maybe there's higher photosynthesis. And if there's cooler at night, then there's less respiration. So you kind of have to like I'm a plant physiological ecologist, and this is just 3 days. You'll see maybe in a minute some more what I actually use. So these were the raw data. Here, when you average the season, maybe I think the month of July altogether, then these were the actual daily profiles that I gave. And so what happened is that obviously it's warmer at midday. I wonder if it shows any of these. Yeah. So you had a greater increase in temperature at dawn than at dusk. And when I'm looking at these and realizing, well, of course, if the midday gets over the photosynthetic temperature optimum, that's not going to make them grow more. And if they have higher night respiration because there's warmer temperatures, then that's also going to take off of any increased growth that you might have with warmer temperatures. And so it might just be that even though you have warmer temperatures in the morning, that should cause this increased growth. Maybe there's growing slightly less at midday and have higher respiration at night. And so we just end up with this net no difference in growth. And it was interesting to me, because there's your photosynthetic temperature optima, and up here you're past it. That's why you see reduced growth. So that if you just add these all up, whereas respiration, it's not polynomial. Like the warmer and warmer you get, it's exponentially more respiration. And so that it just happened that these urban and rural sites were such that these trade-offs all evened out. So it turned out that if you look at, let's see, hide this, enable. So we looked at impact of global warming. Go on to this next one. Here we go. So it turns out, if you look at global warming, and everybody's all focused on, well, what's the average temperature doing? And climatologists just going bonkers, like, okay, we've got all these climate stations, thousands of them all over the globe, and they've all got minute data. And every single station has to take every minute of data and come up with an average for that station. And then every station in every 1 by 1 degree grid cell on Earth has to average all of their one numbers together to get one number. And then all of the grid cells have to average all of their numbers together to get one number for the globe for each year. And that's all the data we get, is just one number per year. So climatologists are like, come on already. We should at least be looking at the daily minimum and the daily maximum temperatures to see what's going on. And they found that the daily minimum temperatures were going up at 2 to 3 times faster than the maximum temperatures. And so, who really cares? It's average, what's the big deal? But if you're a plant, we know minimum temperatures occur at dawn and maximum are in the middle of the day. So so when you change the minimum temperatures, you're really affecting night temperatures more than day. And if you're a plant, you really care the difference of whether it's daytime or nighttime. And so here you are, the plant people are trying to figure out what should happen with these altering minimum and maximum temperature. What should happen? And there's 2 camps. And the first camp says, well, if minimum temperatures are going up faster, then you're going to have more frost-free days you have this, the more realistic asymmetric warming. And so if there's more frost-free days, you're going to have a longer growing season, and you should expect to see increased growth, and that's going to help offset the elevated CO2 problem. And if you look at tree rings and crop yields and satellite NDVI indices, they're all showing increases in growth with warming. And there's all support that that's what should be going on. I'll just introduce this and end. But then there's a whole nother camp that would say, well, with warmer night temperatures, you have higher respiration, and that's gonna reduce growth. And in fact, if you replicate warmer night temperatures in growth chambers, they all see reduced growth because they give a warmer night temperatures. And if you combine the chamber studies, or if you do modeling where you look at the warmer night temperatures and the longer growing season, that the several extra weeks growth for having the longer season never made up for growing less every single night throughout the season. So both chamber and modeling studies would say with this more realistic asymmetric warming, we should see reduces in growth. But nobody knew what would actually happen. And in order to study it, you have to have a precision climate controlled facility where you can control your temperature, CO2, relative humidity throughout the day for you know, every day throughout every year for many years and see what's going on. So I did this big experiment for a decade, looking at, of all things, one factor, which was temperature, and looking at the relative impacts of symmetric warming and asymmetric warming on these grassland ecosystems. And so the treatments then were, hide these controls, were that you would have, you know, just the ambient temperatures, or symmetrically elevated, which is in blue here, where it's 3.5 degrees warmer every minute of every day, or asymmetrically elevated, where the average temperature between the blue and the red line are both the same, but the red line has 5 degrees warmer at dawn and only 2 degrees warmer at midday. So on average, it's also 3.5 degrees warmer. And then just overall ask the question, if you compare symmetric warming to asymmetric warming, do you just see the same result, or do you see increased growth with asymmetric warming, so that's going to offset the elevated CO2, or do you see reduced growth with elevated warming, and so that's going to compound the elevated CO2 problem? And that's the setup for the experiment. And I guess I'll just end here and say, what we found for a long time was the same result, which was difficult, you know, a lot of work for seeing no effect. But then a few years into it, we had a drought. And in the drought, the asymmetric treatment was able to maintain moist longer. And so they had increased growth. So ultimately, what we found with asymmetric warming maintains soil moisture longer and allows for more growth than you would anticipate. So that's the overview direction of where I went. And then I'm going to skip to a very final slide where of just this book, that if any of you ever are going to, in a situation where you're going to teach climate change, I have this, I've been teaching it now for 8 years, and I have this interactive e-workbook where people, you read a little bit, you watch a video, then you answer some questions, and you have multiple attempts to get the questions. So it's a way to learn as you read and to keep you engaged in the reading. Yeah, and it's available. It's on the Top Hat platform. So if any of you are interested to know about that, you could contact me. And that's it.
Awesome. Thank you so much. That was
Okay.
really, really interesting. Brought back a lot of stuff also that I had forgotten from taking kind of earth science, that it's the basics, but they're really important.
Yeah. Okay.
Did you say where could we access this interactive e-workbook?
It's not available. Send me your email, and then it's going to be available in about a month.
Would you mind putting your email into the chat?
Okay.
So yeah, thanks everybody for coming and tuning in. If you are interested in the recording, it should be posted on the NYBG page within maybe 2 weeks, because we have to make sure we get the captions on there. Just a quick note, we will be having next month our the annual EcoFlora conference will be on the 15th of September. We have a bunch of speakers that are going to be there. The theme is the future of New York City flora. So if you are not already on our mailing list, but you want to find out more about that, I'm going to post that link one more time so that you can say get information from us. And with that, thanks everybody, and have a great night and a great rest of your week.